Hey, hi. This is going to be a supplemental lecture for the snow days that we've been having. I want to cover the 2.4 and the 2.5. That's the tail end of chapter 2, deals with some applications. There's a couple of really important concepts that I'm going to call out while we go through this. Otherwise, it's stuff that we've covered already, dealing with right triangles, the trigonometric functions, and the inverse trigonometric functions. But I want to start with some number theory discussion. We have two types of numbers that we work with. Those that come from theoretical work, such as the square root of 2 and pi, these are what we consider to be exact values. Um, there's no rounding in these numbers. Pi has a decimal expansion that just goes on forever. Square root of 2 also. Um, you can't actually ever have these numbers in any type of computer calculation because the digits go on forever, as in infinite, as in if we devoted an atom to every digit in the decimal expansion of pi, pi would beat it. Pi would beat the universe, right? There would just not be enough stuff in the universe to contain it. So it's truly a transcendental number, and that's why they're kind of called that, like E and pi and all these things. Anyway, uh, so what do we do here in our finite world? Well, we measure things, and so the other type of numbers are measured values, and they are not exact. They always represent some range based on the tool that we use to do the measuring. You've measured something with a ruler, right? Um, the distances fall between the graduations of a ruler. So you might have the 1 inch and the 1/8 of an inch mark, right? And your object is going to fall in between those. You can make some estimates as to where it is, but you're really things are fuzzy when you're in between the graduations of a ruler, and that's the nature of a measured value. It's fuzzy. So I always do this example where I look at the projector screen in a classroom. So I've got this big rectangle here, and I measure it. And in this case, I have 15 inches by 18 inches. I think this was a monitor. And then I want to calculate the diagonal, right? Um, what's the distance across the diagonal? Of course, a diagonal is the way TVs are described. If you go buy a 52-inch TV, the diagonal of the TV is going to be 52 inches. Easier to measure, of course, is the length and the height, right? And so for this monitor, we've got 18 inches by 15 inches. And I've noted that there's two significant digits in those numbers because those numbers aren't exact, right? That's 18 inches plus or minus half an inch, right? Because that number that's written down there only implies that amount of accuracy. We measured to the inch. So you can imagine a ruler with graduations that are an inch apart, right? We could do better, of course, but in certain applications, we just need things to just certain accuracies. We'll talk more about that here in a minute. Anyway, so if we want to calculate the diagonal, well, we know that that's a right triangle. Right? You got the right triangle there in the corner, or the right angle in the corner, and 18 and 15 are the legs. So we just square those, add them together, and then take the square root. So you got your 15 squared, your 18 squared, 225 plus 324. Add those together, you get 549. The square root of that is 23.430749. And if you look at your calculator, it would just keep spitting out digits for you, right? Um, the question is, how many should we take? How many digits should we answer to? And some situations you'll just want to take a fixed number of digits. I happen to know that engineering, they have them write down 6 or 8 or something like this all the time, I guess, and let somebody else do the rounding. But we're better than engineers. We're gonna go ahead and do the rounding ourselves. Um, how many digits should we have? Well, if we look at the numbers that went into the calculation, right? We count them both as having two significant digits. I'm going to talk about that here in a minute, like how you compute the number of significant digits. Anyway, they both have two, and so the answer should have two. So we'll just take the two here, 32. And I think it makes sense if the sides were measured in inches, the diagonal should be measured in inches, right? The nearest inch. So 23 inch. So that's a 23-inch monitor. Okay. So diagonal's approximately 23 feet. And that doesn't mean, of course, that the diagonal is exactly 20 feet, sorry, inches. Wow. How did I miss that? Oh, inches. Must be talking about like a drive-in movie screen or something. Anyway,
Yeah, I think we stick with feet. Let's stick. Yeah, I like that.
what's that?
I like feet. Let's go feet.
Yeah, feet, the big screen. Yeah, big screen, movie screen. Yeah. Yes, 22.5 and 23.5. That's what that number means. So 23. It means it's somewhere in between those numbers. That's just tells the reader, how accurate we were in our measurement, right? Now the measurement of the sides turned into a measurement of the diagonal, even though it was computed. Okay, so here's some numbers, and I've written down the number of significant digits, and we're going to talk about like why here. So 408, if that's a measurement, and I guess I missed it at the beginning, but counts, like if you count a number of things, that's not measured, right? If there are 10 sheep, right, there's not like 9.5 sheep to 10.5 sheep, right? It's just that's how many there are, right? However, measured values, that's where significant digits kick in. So 408, if that's measured, then there are three there. You just count the digits. 408, there's three. 21.5, there's three, right? 215. 18.00. Now, some students would say there's two, but those zeros that come after the decimal point would not be there unless they were significant, right? Why would you write them? I mean, what comes after that zero, that last zero there? Well, a bunch of other zeros. Why are they not written? Well, the reason is those are not significant zeros, right? So this number to me, or to anyone, right, should be 18.00. This was measured to the nearest hundred, right? Hundred of whatever, hundredth, I should say. So there's four, right? 6.700, same thing, right? Four, one, six, seven, one, two, and then two zeros, three, four. All right. How about the next one? 0.0025. Now here students will say, oh, there's four, right? Because those zeros, right? No, there are two, right? These zeros that lead off here are just finding the right place value for our number. So 25 in this case. The rule of thumb is if you put the number in scientific notation, what digits would you write? So in this case, we would move the decimal point over three times and get 2.5 times 10 to the negative 3. There's two significant digits, right? If you did that with all these numbers up here, I guess 6.7 is already in scientific notation. 18.00, you'd have 1.8 times 10 to the first, right? Seems they're not really useful for numbers like that, scientific notation. But all right, so zeros before the digits, after the decimal place, don't matter. As long as as long as there's not like a number before that. If there was a one in the tenths place here, then there would be four, right? Because all the digits would be significant. Anyway, so you got to think about that as we measured down to the, what is that? Tenths, hundreds, thousands, 10,000s, right? Okay. How about 7,300? That's a big question mark. Is like, well, is it four? Are those zeros just placeholders and there's two, right? Um, Maybe there's three, right? How do we know? We don't. So we have to be given some context for numbers like these. Um, and so if we're not given any context, we have to assume the smallest number of significant digits in the number. In this case, two is the minimum. So that's what we would assume, that this number was measured to the nearest hundred of whatever's, right? Whatever units. If this was actually measured to the unit, down to the actual unit, then we would have to have some context behind that. Someone would have to tell us, oh, we measured this, got 7,300 exactly, or not exactly, but down to the nearest unit. Story I like to tell about that, and I can go ahead and talk about it a little bit, is Andrew Waugh. Andrew Waugh was part of the Great Indian Cartographic Expedition, and I should probably get a year on that. I'm thinking 1800s. Anyway, so he, with his team, started in India, started on the coast, and measured elevations of hills going inland. Their goal was to get an accurate measurement of the heights of the mountains in Nepal, which is on the north side of India. There are a lot of famous mountains down there. You probably know one of them. uh, Mount Everest, of course, the tallest mountain in the world. There's others. There's Annapurna, which has a wonderful hiking trail that goes around it. I've never been. It's kind of on my bucket list. But anyway, um, how did how did Andrew Wall go about doing this? Well, he took very fine measurements and basically used right triangle trigonometry. We've got horizontal, vertical, right angle, where you are. There's a horizontal distance and then a vertical distance, which is the height of the hill that you're looking at. You do the calculation here, get the diagonal, just like we did for the TV, and boom, you've got that height. And once you have that height, you do that again and again and again, going up the elevations all the way up to Mount Everest. Now he used it was his calculations were a bit more sophisticated than this. Um, he accounted for a lot of things. The curvature of the Earth. He also accounted for the gravitational pull of the mountains themselves. Um, to find vertical, they used a plumb, which is a weight on a string that points towards the center of the Earth. Of course, it points towards the center of the Earth because the gravitational pull of the Earth pulls it downwards. However, if you're standing next to a mountain is very massive, and so it has a gravitational pull, of course. And so that would pull the plumb towards the mountain. Well, Andrew Waugh accounted for that, just to show you how careful he was doing the calculations. In any case, they do this months and months and months go by. They measure all over India heights and elevations. They go all the way up to the mountains, and get the final calculation there for Mount Everest. And he does the calculation and he gets 29,000 feet to the nearest foot. And he's very disappointed in this number, right? And due to our significant digit discussion, we know why he was disappointed, right? Because anyone who looks at that number is going to think Andrew Waugh spent, you know, hundreds of thousands of pounds, right? Back in the day, a small fortune, a big fortune, right? Just to get the height of Mount Everest to be 29,000 feet. It looks like it's rounded to the nearest 1,000 feet. It's like, well, of course, Andrew, well, anybody could go out there and do that, right? It's about 29,000 feet, right? No, no, no. It's to the nearest foot, nearest foot. So Andrew Wall, what did he do? So he can't publish that number, right? No one would understand. So he goes and he just tacks on 2 feet. I'm not recommending you ever do this, but that's what he did. He reported as 29,002 feet. Now, how many significant digits are there? There must be five. It must have been rounded to the nearest foot. You can see it in the number, right? If I just said 29,000 feet, you're like, okay, a plane flies at 20,000 feet, sure. 20,002 feet? Oh, that's pretty precise, right? That's like, oh, that's to the nearest foot. Someone did some calculation to do that. And so that's the number that was published. And to this day, Andrew Waugh is known as the first person to put 2 feet on the top of Mount Everest. I'm glad you appreciate that joke. Yeah.
Solid, solid.
Okay. Well, anyway, so just the thing to remember from that is that you want to use the least number of significant digits among all the numbers in your calculation. Okay. In our context, we're going to be basically solving triangles as our applications. So let's just start by solving a right triangle. Um, Solving a triangle means to find the length of all the sides and the measure of all the angles. I think that's pretty clear. Like, well, what is a triangle? It's just three angles and three side lengths, right? So we just need to find those. For a right triangle, the minimum condition to solve it is two pieces of information. It can be two sides. It can be, well, can't be the two angles because that doesn't give you information about the side. So you need at least one side and then any other piece of information. It's pretty easy to solve a right triangle. We will study all triangles, these are triangles that are not right, later in the course, in the third kind of unit that we cover at the end of the semester, assuming that we don't have any more snow days. So here's a right triangle, and we're given the angle B to be 28 degrees, 40 minutes, and side A, 25.3 centimeters. This is the standard labeling of a right triangle. The side, so the side C or side A or side B, lies opposite the angle. So you see the angle B there at the top. Side B is the opposite side. Like when we calculate the trig function ratios, it's the opposite side. That's what gets the name B. Okay, I think it's clear. And there has to be some labeling to these, and we'd like the sides to relate to the opposite angle. That's just to help us get some organization in that. Anyway, so 28 degrees, 40 minutes, and then the side A there's 25.3. Okay, so what's the easiest thing to find? This easiest thing would be the other angle, right? Since angles in a right triangle are complements, it's easy. 28 degrees, 40 minutes, and that becomes 61 degrees, 20 minutes for angle A. Great. All right. The next thing to do would be to try to find the sides. And we can go after side B because B is opposite the angle. And then the side that we are given is adjacent to that angle that we're given. So those are two side lengths. We put them in a ratio together. We get a trig function. Opposite, adjacent. That's tangent, right? Opposite over adjacent. Or I guess you could do adjacent over opposite, which would be cotangent. However, we're solving for B. We want to find B. So tangent's good because it keeps the B in the numerator. Anyway, so tangent of B is B over A. Angle B is 28 degrees, 40 minutes. So tangent of 28 degrees, 40 minutes is B, side B, over 25.3. And that's easy. You just multiply that 25.3 over, throw that in your calculator, and then you round to the correct number of significant digits. Now, if we look at the numbers, we've got 25.3. That has three significant digits. And then the angle, 28 degrees, 40 minutes, has three also, because we can't assume that that zero after the four is significant. It doesn't really matter because if it was four, we still have the side length measured to three significant digits. So our answer would be to three anyway. So there's no ambiguity here. We're going to answer three significant digits, 13.8. So the answer it turns out to be. Okay. Once you have those two, the last thing to do is to find the side C. And there's many ways to do this. You've got the two sides. You could use the Pythagorean theorem. I would suggest using the given information in the problem. Rounding does come up with errors in certain cases. It's not all the time, but you're just safer using the given material or given information. So if I want the hypotenuse, I'm given the adjacent. That's either cosine or secant. I use cosine because cosine's a button on your calculator. So we'll do this. So cosine of B is A over C, and we will solve for C, and we just trade out the C with the cosine there. Multiply by C, divide by cosine to get this. And then plug in what we know, 25.3 for A, 28 degrees, 40 minutes for cosine, and then do the calculation, answer to three significant digits. We get 28.8 centimeters. And that's it. That's all the sides, all the angles. Straightforward. Okay. If not given any angles, how do we handle that? We've got 25. We've got a triangle here. Side B is 55.87 centimeters. Side A is 44.25 centimeters. And we're asked to find the remaining side, the hypotenuse, and then both of the angles. All right, we can find C pretty easy because if we're given the legs, we can find the hypotenuse just with the Pythagorean theorem. And so that's what's happening here. Both of these are to four significant digits. You can see that. So we answer to four. So the hypotenuse here happens to be 71.27. You know how to do that. I'm not going to go through that. To get the side, or sorry, to get the angle, we're just going to pick a ratio. And since we're given the legs, I'm going to go ahead and use tangent. You don't have to, but that's what I'm going to do. You could go off angle B also. Right? And that's opposite over adjacent. So if we look at angle A here, opposite is the 44.25 and the adjacent is 55.87. So there's that ratio there. And then we want the angle, we use the inverse trig function, arctangent. Right? So tangent of an angle is a ratio. Inverse trig function of a ratio is an angle, right? So it depends on what you want. We want an angle, we're using an inverse trig function. Right, and you can throw that in your calculator and it will give you the right answer, 38.38 degrees. And that's a decimal degree. If you want to go to minutes, right, what do you do? If you remember that chapter 1, right, you're going to take the 38 to 0.38, multiply it by 60, right, to turn it into minutes. So 0.38 times 60, and you get 23 and some change, right? And that's what you report. So we want four significant digits. All right. Once you have that, you don't have to do really any heavy calculation with an inverse trig function because we know the two angles are complements to each other. We just go ahead and set up the subtraction here, 51 degrees, 37 minutes, already to the right number of significant digits. So there you go. That's really all the cases for solving the right triangle, right? You either have an angle and a side or you don't, right? You don't have an angle at all. And if you don't have an angle at all, you need to find them, and it's inverse trig functions that do it for you. All right. We could do the tree problem again, this time without, I think we had a little kid, Joey, and he was measuring his shadow. We don't need that. We just need the distance to the tree and the angle of elevation to the top of the tree. We don't even need the sun this time, right? So the angle of elevation from a point on the ground, 15.5 meters from the base of a tree to the top of the tree is 60.4 degrees. Find the height of the tree. All right, so we have measured the distance somehow to the nearest, what, tenth of a meter, right? So what would that be? 100 centimeters, or no, 10 centimeters, right? So 15.5. We also measured the angle of elevation, 60.4. degrees. Okay. We want the height of the tree. And here the height is the opposite side from the angle that we have. The adjacent side is given to us. So tangent is the ratio opposite over adjacent. Tangent of 60.4 degrees is h over 15.5. Solve it just like we did in the previous problem. We're going to multiply that over, go to our calculator, round to the correct number of significant digits. Looking at these numbers, it's 3, right? It's clearly 3 for both numbers. So 27.3 meters. Pretty tall tree. Okay, anytime you've got an applied problem, try to draw a picture. Sometimes there's just no picture to draw, but if you're measuring the height of things, go ahead and make a quick sketch. Um, really helps organize the information. And it makes sometimes or often it just makes picking the trig function trivial. It's like, oh, clearly I've got opposite adjacent tangent, right? Good. Okay. Another example here. Let's find the angle of depression from the top of a 97-foot tall building to the base of a building across the street located 42 feet away. Okay. So I've drawn a picture here, and let's kind of go through the picture here. We've got a building. We've got the surveyor here on the top measuring the angle. We've got the building across the street, and we know the buildings are 42 feet apart, so I'm going to put that on there. The height of the building is 97 feet. And we're looking for the angle of depression. Now, the angle of depression comes from the horizontal. So if you're looking at the horizontal and then you look down, that is an angle of depression. So this angle I have highlighted here, the theta, right? That is I guess this top theta, this one, right, is the angle of depression. And that lies outside this nice, neat right triangle that we've formed with the angle of depression down to the edge of the building across the street itself, the 42 feet, and then the height of the building, which forms a nice right triangle. That theta, though, does exist inside the right triangle, and it's here, right? And why is it there? With a little bit of geometry. See the observer horizontal, the top of the hill here, this part, right? And the ground are parallel to each other. And then the line of the angle of depression, that line acts as a transversal. And so there are a bunch of angles that are congruent. In this case, the important pair is the um, corresponding angles on the inside, right? So the alternate interior angles, right? So those are the same. Those are congruent. So the theta here exists in this triangle, but it's in the bottom corner. Right? Okay. So we just need to find this angle theta. That gives us our angle of depression. So again, tangent, because we're given the sides. We've got the horizontal and the vertical here, the adjacent and the opposite. So we'll set up our tangent ratio 97 over 42, opposite being 97, adjacent 42. Again, we want an angle, so we need an inverse trig function, 97 over 42, and that ends up being 67. Note the 2 significant digits here on the number. All right, now you could report this as an angle of depression of 67 degrees, or you could say it's like negative 67 degrees since it is measured in the clockwise direction. But calling it an angle of depression already takes care of the minus sign, so to speak. So that's how that would be like reported if he were writing up his report for this angle of depression. All right. More right triangle applications, this time in the context of bearings. This is 2.5. Bearings are how you pick a direction. Like if we're traveling in a particular direction, or there's an object that we're interested in that is often some distance, right? We want to be able to communicate where that is relative to us, and that's a bearing. There are two types. There's an aeronautical bearing and a nautical bearing. I mean, the words themselves tell you where they're used, right? Aeronautical bearings, this is what airplanes use when they navigate around. And nautical bearings, and this is the way ships navigate on the water. Also, land-based travel typically would use the nautical bearing, although either would work. Either would work. Okay. So, how are they measured? Now, they're measured a little differently, or the whole setup for them is different. For aeronautical bearings, start with that. It's a single angle measured in a clockwise direction from true north. Let's look at the first example here. Um, we have a direction. So we've got a starting point. That's the dot here in the middle. I draw the north line on there. And then I measure a clockwise angle in the direction that we're going. In this case, this is a southeasterly direction. And so we would report that as 120, right? 120 degrees, right? And I've drawn some other ones on here. There's 15, and then like 300 over here. Okay, so always in a clockwise direction. And I know that's counter to the way angles in standard position are. Usually we look at the positive, and that's a counterclockwise rotation, but these bearings are different. Excuse me. And different than that. So we just have to keep that in mind. If we're in a bearing situation, this is how it's set up. And it's always from the north line, right? Even if you're traveling south, that would simply be, what would it be? 180, right? East would be 90, right? West would be 270. Okay. So that's just one number to keep track of. Nautical bearings, on the other hand, are an acute angle, so like almost like the reference angle from the north-south line. And that's important. Always from the north-south line. So I went ahead and all these directions that are in aeronautical bearings, I wrote the nautical bearing below it. Let's see if we can make sense of that. So if we're going 120 in aeronautical, the north-south line, right, would be 60 degrees away, right? That's this number here, because that would be the supplement, right? 120 and then 60 is what you would need to get to the south line, right? And so that 60 degrees is the nautical bearing. And we would write it as south. Is it north or south? First, south. The angle deviated away from south, 60 degrees. And then in which direction was that angle deviated? In this case, east, right? So south, 60 degrees east. It tells you which direction it is, southeast. And then 60 degrees is, how far are you away from south? Here at 15 degrees, right? So we're north, right? So we're going up north, 15 degrees is the deviation, and then east, right? Or to the east direction again. And so 15 degrees east. 300 here, that's a northwesterly direction. So north. And then what does this, 300 is almost the full rotation. It takes 60 degrees to go back to 360. So north, 60 degrees west. Just practice with these and you'll get it down. So aeronautical, nautical. Okay. We've got an example here that uses radar stations. So radar stations A and B are on an east-west line, 8.6 kilometers apart. Station A detects a plane at point C bearing 53 degrees. Station B simultaneously detects the same plane on a bearing of 323 degrees. Find the distance from B to C. Okay, so you can imagine this. You've got some area, some region. You've got two radar stations. We happen to know that they lie on an east-west line, and we know how far apart they are. 8.6 kilometers, right, to the nearest 100 meters, something like that. Station A, the first one there, detects a plane with certain bearing, right? That's 53 degrees, so that's an aeronautical bearing, right? We can see that because there's no like north-south on there. Although we know 53 is northeast, right? Since we would go from the north line and then take the clockwise direction by 53 degrees. So put that on there on the picture. Station B detects the same plane bearing at 323 degrees. Okay, so that is a northwesterly direction. We can see here the 323 on the picture. And so we have this triangle formed. And I've already written on the angles, but you'd have to calculate these. For example, this interior angle of the triangle, do I have a different color? Can I do a different color? Let's see. Color would be nice. Orange? Hmm. Yeah. Okay. So that 37 degrees is just a complement of the 53, right? So you can see this right angle here. This one, a little bit harder to compute. So we've got the 323 degrees, right? If we go all the way around, that's 360. If we go three-quarters of the way around, that's 270. So whatever this is more than 270 must be this angle. And you can take 270 minus that. That's what I've done over here, right? And we get our 53 degrees. Great. You got two angles of a triangle. You automatically know the third. So 37 plus 53 happens to be 100. Sorry, happens to be 90, which means the other angle must also be 90. And we're looking at a right triangle. How convenient for us, right? That we have a right triangle. That means we can solve for a side. Okay, and so we just need to find the right ratio. And that ratio is sine. If we're looking at angle A, it would be cosine if we're using angle B. You get the choice there. So sine of A is A over C. We have all those numbers. We want A, we're going to multiply by the C. A is C sine of A. Plug in our numbers, round to the correct number of significant digits. We see that this airplane is 5.2 kilometers at a bearing of 53 from radar station A. Oh, sorry, from B. Sorry, from B. So bearing 323. Right. So that's an aeronautical bearing example. I also have a nautical bearing example here. So a ship leaves port and sails on a bearing of south 34 degrees west. I have a highlighter. So let's use that now here at the end. South 34 degrees west for 2.5 hours. It turns and sails on a bearing of north 56 degrees west for 3 hours. If the ship's speed is 18 knots, find the distance of the ship from port. Okay, so there's the goal, right? Find the distance of the ship from port. Okay. The first thing we want to talk about is what is a knot, right? A knot is a nautical mile per hour. So I've written that here. One knot is 1 nautical mile per hour. But that just raises the question, what is a nautical mile? Um, and so you understand the concept of a minute, right? 1/60th of a degree. So if we take the Earth here, go from the center of the Earth to the surface, and then we deviate that radius by 1 minute as a degree, the arc length swept out is 1 nautical mile. So a nautical mile is 1 minute of latitude on the surface of the Earth. Latitude is the north-south. Right? Um, that it makes it a little bit longer than a statute mile, the 5,280 feet. It's a nautical mile is a little bit longer. It's 15% longer, ish. It's not exact here. So 1.15 statute miles is 1 nautical mile. And then a knot is just a rate of speed. It's nautical mile per hour. Okay. So this problem gives us the bearing of the ship at certain points in time and how long it traveled on that bearing. And with the rate, we can then get the distance traveled. And so I've created a picture here. We've got port. We've got the bearing of 34 degrees south, 34 degrees west. So that's here. And so the ship ends up here after the 2.5 hours. You could take 2.5 times 18, and that ends up with 45 nautical miles. So the ship travels 45 nautical miles in the southwesterly direction, turns north 56 degrees west, and that is this number, and the 56 degrees west. So I've got my north-south line for the new position of the boat. Go up to the north, deviate 56 degrees to the west. There we go. Boat travels 3 hours on this path. 18 knots gives us 54 nautical miles. And there's the boat. Always got to draw a boat. Little sail, ripply water. Anyway, there we go. Okay. You can see a triangle is formed. We're interested in the distance back to port. So that's just drawing a point from the boat back to the port. And 56 and 34, right, happen to be on this angle here. And that 34 and this 34 are the same because you've got the alternate interior angles, right? The north-south line from port, the north-south line from the position of the boat after 2.5 hours. The path of the boat is a transversal. And so those alternate interior angles are the same. So this angle of the triangle in the bottom corner here has 56 and 34 added together to make up that angle. That happens to be 90. So again, a very nice situation for us. All right. We'd like to find the distance here. And since we're given the legs and we know we have a right triangle, we can just use the Pythagorean theorem to find it. So really, the trig was just involved in proving that we have a right triangle. Throw that in a calculator, you get 70 nautical miles. You want to state that we know that's to the nautical mile, right? Not to the 10 nautical miles. But anyway, that's how far the ship is from port. Okay, if you want to go further, you could find the bearing of the ship to go back to port. And that's something that we could do with an inverse trig function. And I don't have that written down. I don't want to try to do that, but you can try to get this on the screen here. But you could do that if you wanted to find the distance. All right. Okay, that's really it. That's 2.4 and 2.5. I wanted to also talk a little bit about the test review and all that, since we're not going to have it, not going to have the test coming up in the week when we come back, if we come back. I don't know what's going on with the weather, but on Wednesday next week, we're just going to start chapter 3, and we might take a little bit of time to review for the test coming up. So that gives you another week from all spaced away from all this nonsense, so that you can, you know, uh, have access to me and the resources at the college for another week. Anyway, so what do you want to do to prepare for the test? Well, the questions that are on the test are the same type of questions that you see on the homework, same as the examples I do in class, and the same as the examples you find in your book in the sections and also in these review areas of the book. Now, this book that we use is great in terms of test prep. Every The end of every chapter has a list of vocabulary, a list of the sections, the topics, and an example problem from that section with references to the review exercises for that concept. It's great. I really like this book for that reason. Um, and so here are the page numbers for the chapter 1 and chapter 2 test prep. You'll find all those resources on those pages. You can also find this on the ebook. It's the same page numbers, I believe. Pearson also has other review tools. So there are like quizzes you can do. You can create your own assignments in there. You just go to the study area there in Pearson, and you can find all those resources. So the test prep for chapter 1 is on page 157. Review exercises follow. The test prep for chapter 2 is page 209. And like I said, we'll go over some material at a future session. We'll talk just briefly about it on Wednesday of next week. Okay, well, I appreciate you listening to this lecture. And if you have any questions, please reach out. I've got office hours. You can send me a message through Canvas. You can also go to the math lab. The tutors there know their trigonometry. So please take advantage of those resources.
Thank
Okay.
you. Uh, Quick question on the test on some of the review on the online resource.
Yes.
Anyway, there's like a couple questions that ended up requiring a graphing calculator. I just didn't know if that would be something that would be on the test, specifically the graphing calculator.
Okay, thanks. Yeah, that's a good question. No, there's not going to be anything that requires a graphing calculator. I don't think on any of my tests.
Okay,
So
sweet.
yeah, you will not need a graphing calculator. And those are great resources. We will be looking at the graphs of trig functions in chapter 4. But we'll be doing those by hand because we'll want to be able to look at a trig function and identify its features without looking at a graph. Now, it's great to have a graphing calculator, or you can go to like Desmos, which is an online graphing calculator, to see it. It's always good to see it, but it's not going to be required for a test. But yeah, that's a great question.
Okay, well, thank you.
All right. Thanks, Tristan, and I'll see you all next week.